Hello and good afternoon, everybody. So now we are continuing with our class entitled Igneous and Metamorphic Petrology. So this is now just a more detailed overview into igneous and metamorphic petrology. And it is actually the step-in course then for the 4th-year class, which is entitled Igneous and Metamorphic Petrogenesis. So now at first we will just start with the introduction, and here I would like to start with some basic facts about the Earth. So we have here a picture with the Earth's internal layered structure, or showing the Earth's internal layered structures. So, and I'm using the textbook from Gautam Sen. It is available in my office, and there in table 1.1 you will then find the thickness and the text for the composition of these individual layers. But here for now we have this picture. I'm trying to explain to you the picture. So we have now when we are going through the Earth from the core to the crust, then we have following different layers. Very in the center we are dealing with the inner core, yeah. The inner core is surrounded by the outer core. Then we have the so-called D layer, which is also seismic boundary. Then we have the lower mantle here. Here we have the lower mantle. Here we have the transition zone between the lower mantle and the upper mantle. Here the upper mantle, and then above we have the crust. So, and the crust can be subdivided in the oceanic crust and in the continental crust. So the upper mantle and the lower mantle is anything else as homogeneous. And I mean, just 20 years ago, people or scientists still thought it is more or less homogeneous, but newest results on research show that the upper mantle as well as the lower mantle is anything else as homogeneous. So, and Earth is a differentiated planet, yeah. So the continental crust, for example, is very felsic. The oceanic crust is more mafic. And when we are going down into the upper mantle and lower mantle, then it becomes more ultramafic, or in the lower mantle we are talking about a composition like a rhyolite. And the rhyolite I introduced to you last semester, that is experimental and theoretical chemical composition, and this chemical composition from the rhyolite is close to that from a lersolite. So going now to the next slide, we have now the formation of the solar system from a nebula, yeah. So we have now a cloud rotates and contracts, yeah. And this cloud is rotating around an axis. So, and due to this rotation, the cloud flattens while it is rotating, which we can see in the next picture, yeah. So, and then we are forming later on concentric rings. So, and then that was then the first 3 steps, and then we have then the formation of a protosun, and this protosun is surrounded by the planets, yeah. So, and that is then the formation of the solar system, just in a few words, out from a nebula, yeah. Like we have our solar system, yeah. We have then the sun in the middle, then we have the 9 planets, we have 4 rocky planets, 5 ice and gas planets, whereas planet number 9, that is Pluto, which is the smallest one, is flying in another orbit, or it has another flight route. So, and there are scientists, they are saying or claiming that Pluto is not a part of our solar system. And I think it was now in 2010 or something, it was then finally removed from our solar system. So, but if you are looking in older textbooks there, Pluto is still a planet belonging to our solar system. So here we have now a nice picture here, yeah. And that is just a nice fancy illustration how the moon was formed, yeah, 4,500 million years ago. And the moon was formed by a collision of a Mars-sized body, yeah. You know, the Mars has a diameter of 6,000 kilometers, and the Earth has a diameter of 12,000 kilometers. So when Earth was struck 2,005 or hidden 4,500 million years ago by a Mars-sized body, then this was quite a huge mass, or a huge volume and a huge mass, and that leads then to the flip of the Earth's axis, yeah, and to the formation of the moon. So here we have now three slices. We have the origin of the Earth by accretion of planet-forming materials. The heterogeneous accretion model calls for accretion of already differentiated asteroid-like bodies. Yeah, these are asteroid-like bodies. Yeah, so here we have the asteroid-like bodies. Whereas homogeneous accretion models suggest the formation of a proto-Earth from undifferentiated planetesimals. Yeah, that is the heterogeneous accretion with some bodies from outside, asteroid-like bodies. So, and then here we have the homogeneous accretion, and that is then by the formation of proto-Earth from undifferentiated planetesimals. The newly accreted proto-Earth was much smaller in the size than Earth we know today. Early in its history, the Earth underwent a major heating event when metallic iron melted and sank to form the core, whereas the lighter silicates were left behind at higher levels or moved up. Yeah, I told you just before, Earth is a differentiated planet, so we have an iron nickel rich core, yes. So, and then we have more silicate, more lighter material at the outermost rim, yeah, and very at the outermost rim we are forming the crust. So that means the crust is forming by the rising of silicates, yeah, because they have a lower density, and the core is formed by sinking iron metal droplets into the center of the former homogeneous Earth. Yeah, so at the beginning Earth was homogeneous. Differentiation processes has taken place, and therefore we have then the formation of the core, the inner core, the outer core, which is very rich in iron, nickel and cobalt. Then you have the upper mantle and the lower mantle, where we have already a lot of silicate minerals. Yeah, olivine is the most dominant mineral in the Earth's mantle. And then we have above the formation of the crust, and the crust can be again subdivided in oceanic crust and continental crust. So here we have another very nice picture. We have Edgy's hypothesis by that was produced or was published in Nature in 1990, and that calls for a complicated evolutionary history of the Earth. So number A, we have the early formation of an iron-rich silicate magma ocean and of the molten protocore. Yeah? So here we have at the beginning a very iron-rich magma ocean, and this iron-rich silicate magma ocean, we have then the formation of an iron-nickel-sulfur consisting melt. Then at B we have at some point the mineral magnesiowustite, that is just MgO, with considerable amount of Fe in solution, formed and segregated to form a shell around the core. Yeah? Here we have then this shell around the core consisting of the mineral iron-rich magnesiowustite. So, and the separation of this mineral from the magma ocean caused the depletion in FeO in the magma ocean, yeah? So we are concentrating a lot of iron then in the melt, then this iron-rich core was separated, so and that leads then to a depletion of iron in the magma ocean. Then number C, at number C we have then a molten core which contains a lot of iron, nickel, sulfur and oxygen. Then we have this molten core is surrounded by magnesiowustite. Then we have a layer of perovskite again, and afterwards we have then our magma ocean. So let us just repeat what is written here at point C. Then formed the silicate mineral perovskite, yeah, and the perovskite has actually the same composition like an autopyroxene magnesium iron SiO3, which is the dominant constituent of the lower mantle today. The magnesiowustite layer became smaller because it lost then iron to the core. The core became enlarged. Note that the stages B and C may have happened sequentially or simultaneously. So then we have now the D, and D is actually the situation, how it looks today. We have the inner core, yes, and then we have the outer core. Then we have the lower mantle, and in the lower mantle we have the dominant mineral perovskite. So, and then we have the upper mantle, and this stippled line, that is then the transition zone between the lower mantle and the upper mantle, and the upper mantle is has a layer-solitic composition. And the major or main rock-forming mineral in the upper mantle is the olivine. So, and then very at the top we have the crust, which we can subdivide in an oceanic crust and in a continental crust. So now here at the top you can see there is something cutted away, but it doesn't matter because I will upload the PowerPoint for this class then also on Moodle, and then you can download the PowerPoint and can watch all the figures again and comparing it with all these things what I'm telling you while I'm teaching you here. Yeah. So now we are flipping to that side. What we have here, we have here a cross section through the or not a cross section. It is just an overview map from the Earth's surface. So in the Earth's surface showing then showing only the major plates. So we have then this division of different plates. Here, for example, we have your African plate. Yeah, here that is the African plate. We have here the We have here the Indo-Australian plate, we have here the Antarctic plate, we have here the We have here the Naxa plate, the Cocos plate, here we have the Pacific plate, here we have the Eurasia plate, and here we have the North American plate, and here this small one is the Caribbean plate. So, and here it's written, plates are continents that are shown in gray. Yeah? You have the African continent, or Euro-Asian continent, the Australian continent, the South American, the North American, and you have also the Antarctica. Yeah? And these continents are here shown in gray, and colorless areas, these are the oceans. So, and here we have the divergent plate boundaries, then we have transform faults, yeah. Here we have, for example, a divergent plate boundary that is actually the middle ocean ridges. Then we have a transform faults. A transform fault we have then here, yeah, in California. There we have a huge transform fault. So, and then we have this is shown in light green lines, yeah. So, and then we have convergent plate boundaries, and these are shown here in the dark lines, like here, yeah. That is a divergent plate boundary. Therefore, we have, for example, the subduction from oceanic crust or from an oceanic lithosphere beneath a continental lithosphere, but it can also be the subduction from one oceanic lithosphere beneath another oceanic lithosphere. So yes, and the small dark triangles on them point toward the direction of the subduction, and the arrows shows the overall direction of the plate movement. So now we are going here to inset number A. We have here the Middle Ocean Ridge, yeah. Here and in the Middle Ocean Ridge we are producing new oceanic crust. We are producing on a daily basis new oceanic crust, yeah. And here we are sitting on a divergent plate boundary. And one part of the crust moves here to the right hand, and the other one is moving to the left hand, just apart from each other. So then we have here number B. We have here a convergent plate boundary, so that we have the subduction from an oceanic lithosphere beneath another oceanic lithosphere. Then here in the mantle wedge, we will produce magma. This magma rises up, and at the top we are forming then the volcanic chain. So in number C, we have then a transform fault, yeah, like we can observe it in California. So these are the major boundaries which we can find on Earth. So in at these boundaries we have the formation of igneous rocks, and we have also the metamorphism of rocks. So they are related very closely to each other. So then, if you are looking at our planet, then you will see we have now all the continents, and the continents are separated from each other, but that was not always the case through Earth's history. So we have always the formation of supercontinents and the breakup of supercontinents. So the first supercontinent, that was Valbara. So and that was about 3,300 million years ago. There Valbara exists. So the formation of Valbara started maybe 3,600 million years ago. Then we have the finalizing of the Valbara was maybe 3,300 million years ago. And afterwards we have the breakup of Valbara. So now, if you like, that was a long time ago in the Archean time, yeah. So, and if you like to know something more about Valbara, then if you like to study rocks from Valbara, then you have to go to South Africa into the Kapval, yeah. So, but we have also outliners of the Kapval here in Namibia and in Botswana, yeah. But the most prominent area of the Kapval, that is in South Africa, and the other parts of Valbara, that is then the Pilbara, and remnants of the Pilbara you can find in Western Australia. So, and these are the remnants of the first continent, of the first supercontinent. So then later on, during Archean time, about 2,500 million years ago, you had a supercontinent, Columbia. And during that time, let us say between 2,500 million years and 2,800 million years, you have an enormous growth and formation of continental crust, yeah, of newly formed continental crust. So then you had about 2,000 billion years ago, you have Nuna land. There you can find remnants nowadays in Korea and China. So then you have later on at around 1100 MA ago, you had supercontinent Rodinia. Then about 500 to 600 million years ago, you had the formation of supercontinent Gondwana. And then here, 200 million years ago, the landmass was also again together. We had the formation of supercontinent Pangea. So you have always the formation of the supercontinents, and afterwards you have the breakup of the supercontinents, yeah. So in the formation of the supercontinents and the breakup of supercontinents mainly control the natural climate change, yeah. Everybody is nowadays talking about the climate change and too much CO2 emission and which is all true, yeah. But we have also a natural climate change, and that is when the continents are apart from each other, or when a supercontinent breaks up, then the temperature rises always up, and the CO2 emission rises also up because of the increase, or because the magmatic activity will increase normally, and then you will increase the internal heat from the planet. So nowadays, I mean, we are in a hot phase, yeah, and because the continents are apart from each other, but the time will come. We have already started to form now the next supercontinent, yeah. That means the whole landmass is then again together. So, and then it becomes very, very cold, yeah. So then it becomes naturally again very, very cold. I mean, we have scientists have calculated that in about 35 million years, the Mediterranean Sea will disappear. So because the African plate is moving towards Europe, yeah. So then, and therefore, we will form more and more due to the movement of the continents. We are working on the planet itself is working again on the formation of a supercontinent. So, and then the temperature goes down. I mean, if you are going 600 million years ago back, we had a snowball Earth. I don't know if you have heard about snowball Earth. That means the whole planet was covered under a thick ice sheet. So, and we had temperatures about minus 50 degrees Celsius, and there was no life possible. Yeah? And this ice sheet was up to 5 kilometers thick. So now we have here different volcanic eruption or volcanic different formation of different volcanoes, and these volcanoes they have also a certain chemistry. So, and here for example we have as an example the intraplate volcanic chain in the Pacific Ocean. You have all of you have heard about Hawaii, yeah? Here we have the Hawaii volcanic chain, yeah. So, and here you have again some chains. So, and here we have hotspots. So, in such an hotspots, that is the Hawaiian Imperial volcanic chain in the middle of the South Pacific of the Pacific plate is highlighted, yeah. So that means the oceanic crust at the top as well as the continental crust is moving, and the lithosphere and the asthenosphere below is the lithosphere is moving and the asthenosphere is fixed. So, and then we have here just somewhere a rising up plum, that is the source or the plum, and this is stationary, and your lithosphere above is moving, and then you are forming a volcanic chain. So, and then you have here, of course, these volcanoes which are not long feeded by the hotspot. There we are talking about extinct volcanoes, and here where the hotspot is just sitting beneath, we have then an active volcano. So, and these are the hotspot chains. So, and then and Hawaii is actually one, or is actually the biggest hotspot chain on this planet. So, and then we can just repeat here, intraplate volcanic chains in the Pacific Ocean. The Hawaiian Imperial volcanic chain in the middle of the Pacific plate is highlighted. Yes, that is here highlighted. There we can see it with this black line. This chain is thought to be a hotspot track with active volcanism occurring in the big island of Hawaii. So, and that means the hotspot is now sitting here beneath, and there we have the big island of Hawaii, and there we are forming an active volcano. Where Kilauea and Mauna Loa, two of the world's largest volcanoes, remain active. So, this block diagram shows how volcanic chain develops as a plate moves over a hot spot supplying magma that form the volcanoes. The Hawaiian Imperial volcanic chain is thought to have formed over at least 90 million years ago, as the Pacific plate migrated over a relatively fixed hot spot. So, and that is here you have your fixed hot spot, yeah? Which now resides beneath the active volcanoes on the Big Island. Yes, and the active volcanoes on Big Island, that is then Kilauea and Mauna Loa. As the Pacific plate migrates away, a new volcano begins to form atop the hot spot, whereas the old one becomes extinct, it migrates away as piggyback riders. Yes, the piggyback riders. So that is now the Hawaiian hotspot chain. We are going now to our next slide, and our next slide shows us again an overview map from planet Earth. So, and here we have an overview map of the large indigenous provinces and hotspot tracks that connect from the known hotspots. So the origin of large indigenous provinces. It is believed that episodically large plume heads rise from the deep mantle and melt when they reach the base of the lithosphere. Such melts or magmas give rise to large indigenous provinces, such as the Deccan Trap in India. Here we have the Deccan Trap, and here we have Réunion, that is a volcanic island, and that is a hotspot track here. That is the hotspot track. So and nowadays, the hotspot is sitting beneath Réunion. So and formerly it formed then the Deccan Trap here. The tail of such a plume persists for many million years and creates then volcanic chains. So, and here we have then the Hawaiian volcanic chain here, yeah, that is here. Then you have here the Ontong-Java Plateau and the chain here. And then we have here the Bengal Trap and Kerguelen here. Then we have we have here the Marian. Then we have here the Tristan Trap, here we have the Etendeka, and here we have the Parana basalts, yeah, and here we have then the Walvis Ridge. Then we have here the Galapagos and the Caribbean flat basalt, here the Great Meteor, and here the Azores, and here we have Iceland and some flat basalts here on the east, and here in the west. Yes, and that's it, yeah? So, and we will discuss then more in detail later on, then maybe in the 4th year class, then the example of the Parana basalts and the Etendeka. So next illustration shows us an equatorial cross-section of global mantle circulation based on seismic tomography. Is shown here. We have here the subduction of lithosphere, that is in gray. At Sumatra. Then New Guinea and the western continental margin of South America. These downgoing slabs bend sharply at the bottom of the transition zone at 660 kilometer. So, and the boundary at 660 kilometer is here shown with the stroked line here, yeah, with the stippled line, that is this one, yeah. There we have the boundary of 660 kilometer, yeah, dashed, which also marks a sharp discontinuity in mantle material and composition properties, yeah. There we have it. So, and at this boundary at 660 kilometer, our dipping slabs can reside quite for a long time. So, and these old slabs accumulate at the core mantle boundary, and the core mantle boundary is just here, yes, and then all this old material is hanging around there at the core mantle boundary and makes some troubles. So, and then we have here at the core mantle boundary, we have then two thick layers shown as stippled, characterized by large negative shear wave velocity anomalies, that means presumably they are hotter, occur between these antipodal slab burial grounds at the core mantle boundary. Yeah? It has been suggested that mantle plums here in red, these are the mantle plums here in red, yeah, rise from the boundary region of such low velocity layer at the core mantle boundary. Yes, they are rising just up, and this material is then just actually molten material from these old subducting plates. So now we have here another nice illustration. We have here a different volcanoes and different geotectonic settings which are demonstrating the Wilson cycle. So in the Wilson cycle starts then just with such block diagrams from A. This is A, this is B, that is C, and that is D. There it starts. We have then at first plum activity in the asthenosphere. We have the rise up of melt from the asthenosphere into the lithosphere, through the lithosphere, and we have a domal uplift. So, and here within this domal uplift in number B, we have a radial fracture development, yeah. So that means we are at the plate starting here, moving in radially, yeah, as it is shown in C. So, and then we are for making the opening of an ocean basin will be the consequence, like it is shown in D, yeah. So in E we have then just a geological map from the Arabian plate, the Nubian plate, and the Somalian plate. Then we have here the East African rift system, more in the south. Then we have between the Arabian and the Nubian plate the Red Sea, and in the Gulf of Aden we have here the boundary between the Somalian plate and the Arabian plate, and that is just such a thing. How it looks like then in the field. So here we have such an opening of an ocean basin. So, and if you are going then to, when we are opening something somewhere, then somewhere else subduction will take place, yeah. For example, then somewhere else we will have the closure of an oceanic basin, yeah. Like it is shown here in G, we have here the subduction of an oceanic lithosphere between another continental lithosphere here. So, and therefore we are closing here an oceanic basin, and plate X will collide finally with plate Y. So, and this collision continues and continues, so until plate X is molten together with plate A. The slab from the former oceanic crust will break off and sink to the ground, and in the collision zone we are forming here a mountain belt, yeah? So we have always the opening and the closing, opening and then the closure, yeah, of oceanic crust, and then the closing we will not only opening of oceanic crust, I mean we have the opening of some crustal of a plate, of a plate caused by volcanic or magmatic activity, like it is shown in B to D. So as an example, we have E, and then there we are forming the new crust. So and then we have the recycling of oceanic and continental crust, and that is then just in collision zones, like shown here in picture G and H. So now we are going to the next slide. So what we have here three stages. We have here a model, the model of large plume-initiated rifting, flat basalt formation and separation of continents by White and McKinsey in 1989 is schematically depicted here. So at stage 1, we have a plume emplacement beneath the continental lithosphere. So here we have the rise up of a plume, yeah? And this plume will become emplaced beneath the continental lithosphere. At stage 2, we have then the uplift and the erosion and drifting of the lithosphere, yeah? So the lithosphere is thinning, yeah, it becomes more thin to a half. Its thickness is required before partial melts, magmas form in the plume. These melts then erupt through the rifting forming flat basalts. So in these flat basalts we have then here at the top, yeah? And here we have the rifting. So in stage number 3, we have here a plum residue, here we have a plum residue, here we have a continent with the flat basalt above, and here we have a continent with the flat basalt above, and here we have the ocean in the middle. So, and that is then stage 3, continents eventually split, and the plum residue get attached to them and move laterally away as asthenosphere rising and melts, producing then the basalt. So in that we can see along many passive continental margin. And this can be proved by seismic reflectors have been found that they have been interpreted to be dipping flat basalts interclated plated with shelf sediments. So and then we have here this picture from stage number 3. So and here we have here a continent, then we have here ocean in the middle, yeah. So and here we have a continental flat basalt, and here we have a continental flat basalt. So and now I have the question, where can this cross section from stage number 3 be applied? So where exactly on this planet you will find find an example for this correlation. You have here at this side, you have a continent, at this side you have a continent, then you have there an ocean, there you have a continental flat basalt, and there you have a continental flat basalt. So, and I'm sure that you can answer this question very, very easily, where we can observe on our planet, exactly this constellation. So we have here now a velocity anomaly diagram here in percentage. So where we have reddish areas, we are going down with the velocity. We have then a mean, we have slower P waves. and at these dark blue areas we have faster P waves, and in the yellowish areas it's neutral. Yes, red zones are lower velocity, we have hotter areas, and blue areas, they are slower, and there we have then colder zones. So, and then that is always when we are doing some seismic work, we can measure the speed of our P waves and S waves. So, and then we can figure out if these P and S waves, if they are showing the speed as they are supposed to be, or we have anomalies. Anomalies means then if they are slower or faster. So, and when they are slower, then we have, or when we have a lower velocity, then the area is hotter, that means we have melt there. So, but that is now not completely correct, because everywhere where you have hydrated areas, like in a subduction sequence, in a flat subduction sequence, then you are getting also lower velocity values. So now we have here figure 1.14. We have a numerical simulation model of cycling of stages of normal Mendel convection. Yeah, we have 0 million here, that is now. Then we are going 114 million years back. There we have a continental breakup. So, and for example, the opening of the South Atlantic, that was at this time, you know, when Africa was separated from South America. Then we have here the next slide, 152 million years back. We have thermal insulting effects, yeah, because we need a heat source for the opening of a bassin. Then 375 million years ago, we have then a collision zone. Now we are going at first 237 million years back. Then we have the subduction at the continental margin, yeah. So, and this we had in 322 million years as well. And 375 million years ago, we had then the subduction. So we have here actually one whole Wilson cycle, yeah. So now we have another very nice picture. We have here the ABC. So, and there we have thermal insulation models of flat basalt volcanism, splitting of continents, and the formation of an ocean bassin. Heat builds up in the mantle beneath a large continental landmass, like Pangaea. Pangaea was a supercontinent. So, and then we have here the crust above. So then we have here beneath, we have the lithosphere, and here we have the asthenosphere, and there we have, we are building up heat there. And while we are building up the heat there, we will go to figure number B. Partial melting will take place. So, and this partial melt will rise up through the dike system to the surface, and there we are forming a flat basalt, yeah. So, and then we are separating the two plates from each other. We are forming a middle ocean ridge. We have on the left side and on the right hand, we have our continental flat basalts. This plate will move to that side, this plate will move to this side. So, and there we are separating now a continent, yeah. So that was now so far just some very, very general stuff for the how is it called, some basics about the Earth, yeah? So now we will continue with the introduction to inchless rocks, part number 1. Moment, I have to go to the bathroom.